So the first design factor that we're going to talk about today is the battery's grid. Like rebar in a concrete structure, a battery's grid provides the structural strength for what comes later. Battery grids can be cast or expanded, they can be thicker, they can be thinner, they can be flat, or they can be tubular. So there's many different ways to produce a grid to provide that structural strength to the battery's active material. So grids utilized in the production of transportation batteries use three main technologies and one minor technologies. The three main technologies are expanded metal, punched, and continuous casted grids, and the one minor technology is the old technology from 30 or 40 years ago, which is gravity casted. So the driving force behind the expanded grids or punched grids or continuously casted grid is economics. So it's about how can I produce more plates for less and less money at the same period of time. So a plate that I can produce 200,000 plates per day on a certain machine has economic advantage over a plate design that only allows me to produce 50,000 plates a day. So a lot of it is driven by economics. Generally speaking, all of the grid designs that are used in the transportation or starting battery industries are good. Everybody's going to argue that one design is a little bit better than another, and we'll talk a little bit about what makes one design a little bit better than another in certain applications. But ultimately, the three main designs of plates, the designs that we're using today is driven by economics and accountants. So to get a little more in depth into the grid designs for starting batteries or transportation batteries, let's talk a little bit more about the benefits and features of each grid design. Remember that the grid provides the structural strength for batteries, and all of them are generally pretty good. And also, a design that any one particular manufacturer uses over another is often dictated by economics. But if we focus in on each particular continuously produced grid a little bit more, we can determine which features are better, or worse in each one of those designs. So in the case of expanded metal grids, the big positives are, okay, you've got a narrow diamond design. During being produced, the surface is textured, which allows for better active material adhesion to optimize the discharge and charge process. When you talk about, well, what do I mean by textured surfaces or tensile strengths? Well, if you ran your finger along this grid, you can feel that it wants to stop my fingers. It wants to catch my fingernails. It's like when you're painting your car. If you went out and just put paint on over the existing paint, you could expect that paste or that paint is going to fall off that car real easily. It's why when you repaint a car, you rough up the body or you paint a wood door, whatever it is. You sand that first to create a rougher surface so that it will hold the paint. So when we're talking about any particular grid technology and the textured surface or the tensile strength of that design, it's all about its ability to hold the active material that we're going to be pasting onto that plate. So expanded grids have better active material adhesion, and the downfall that people often speak about is that they're not a full frame grid. So as the grid gets older or the battery gets older, there's a tendency, because batteries are alive, they'll grow. This positive plate wants to push up on the corners. With a full frame grid, you've got a frame down the edge here that kind of keeps that structurally intact. When you're producing batteries using expanded metal grids like this, in the production process, you'll put hot epoxy across the top of the cell that helps to hold that plate down. So in an expanded metal element made up of a number of plates, you'll see epoxy placed along the cell here and on the other side, and that helps to resist the growth of an expanded metal grid upwards. And you don't want it to grow upwards, because if it grows upward, the positive plate can short out on the negative cast-on strap later. Punched grids, so the grid that probably or arguably is produced at the highest volume and at the highest rate, allows for real thin grid designs, for lots of cold cranking amp, because you can get lots of those plates in that particular cell. It's a stable design in that it's a full frame grid, but you can't get as much active material onto that full frame grid as you can with an expanded metal grid. Continuous casted grids, so con roll or con cast grids, are a great, as we said earlier, compromise between the two. It has a textured surface for better active material adhesion, and it provides a full frame, so it helps against end-of-life characteristics of that grid trying to rise up at the corners later in the battery's life. So before we leave the discussion of grids and move on to active material and paste, it's important to understand this. So in a battery design, the grid is what provides you with all of your cold cranking amps, or with your ability to move current. So the more surface area that you have by way of grids determines how many cold cranking amps you have in that battery. So the grid, the square millimeters or square inches of grid surface area, is mathematically what will determine the cold cranking amp of your battery to be. So if you have 10 of these grids in one battery, and the grid surface area gives you 50 cold cranking amps per grid, 10 of them will give you 500 cranking amps. If you want more cranking amps in your battery, you want more grids. Alternatively, if you're less about cranking amps and you're more about capacity or reserve capacity and amp hour and reserve capacity do not come from the grid. Amp hour and reserve capacity come from the active material that we're going to talk about next. Grid and the grid wire design that we've been talking about a little bit here, it's really boils down to determining the effectiveness of that grid to hold the active material during pasting. It can affect the efficiency of the curing and formation process that we're going to be talking about a little bit later, and it can affect the overall cycle life and electrical performance of the battery. So a punched grid design that has a flat surface has very bad tensile strength. A concast or con roll grid wire design has a reasonable tensile strength, so it holds the paste pretty well during the pasting process. And the best overall tensile strength comes from an expanded metal grid because it's got the wires are not just flat, but they're also twisted like in a diamond kind of a feature. So it works well at holding the paste when you're pasting those plates. And remember, I talked about its speed. In the battery production process, it's about hundreds of meters a minute of these plates running through the production process. So think of what type of plate would actually grab the paste when the plate is being pasted the best, when it's moving at really high speed through the pasting machine after the grid has been formed. So if you're going to go at a really high speed, the odds are you don't want a plate that has high tensile strength, because it's just not going to work very well. So particularly if that paste is going to be a drier paste, like what we might use in a deep cycle battery versus a wetter paste, like what we might use in a starting battery. So think of the battery production process in terms of speed, in terms of tensile strength, the ability of the plate to hold paste as it's being pasted onto the plate. So if this plate is ripping through those pasting machines at 250 meters a minute, it's pretty easy to comprehend that it's not going to be able to hold a lot of paste. And that paste is going to have to be pretty wet, or you're not going to be able to run those plates through there very fast. So the grid design, the grid wire design will determine the effectiveness of the adhesion of the paste, the overall efficiency of the plate during curing, and the overall cycle life of the battery later on. So when a pasted grid is cured and dried, the active material wants to shrink and generate forces at the grid wire that force the paste to separate from the grid wire. So when we talk about tensile strength and we talk about active material adhesion, what plate design or what grid design is better for active material adhesion, there's some different tests that we do or that can be done by anybody, and it's what we call a drop test. So this is a grid, and this is the same grid but pasted. What we'll do is actually take these pasted plates, and from a height of 1 meter, we will drop them. And we do that 9 times. That'll show you which type of grid actually will hold the paste better. So in our tests, expanded metal grids prove in the drop test that they have better tensile strength and that they will lose less active material after being dropped 9 times. So in summary, as it relates to grids, I mentioned earlier that I would keep coming back to using concrete and rebar as an analogy to building a battery. But like steel in concrete, grid design will determine the final strength and durability of the finished plates.